So, in the previous class we had a introduction to shock waves, and we learned that these waves, shock waves, are present only in supersonic flow. This is something that you have to bear in mind throughout this course, that shock waves exist only in supersonic flows. We saw through simple kind of examples or analogous example that presence of nonlinearities actually sort of allow compression waves which are not really very strong. These compression waves can coalesce with each other due to a process known as wave steepening. This is because of the nonlinearities in the flow, where flow variables are affecting each other, and the solution is dependent on flow variables, and because of that they coalesce to each other and form a shock. And shocks are very thin. So when we look at gas dynamic analysis, we do not actually consider these shock waves in the but they are considered as discontinuities, so they are not considered in solving the flow field and things like that, but as discontinuities. So jump conditions across the shock is what is applied when shocks are found in a flow field. So now we have to analyze these jump conditions across the shock. So across a shock, pressure, temperature and density increases, and velocity decreases, Mach number decreases. So that is the essential picture. So now we will apply the conservation equations across the shock, and here shock is treated as a discontinuity. It is extremely thin. You do not calculate the structure of the shock wave. So this is the schematic representation that is given here, that you have a very thin shock, and before the shock these are conditions. This is upstream, and this is downstream. So you consider two states, upstream and downstream of the shock. For sure the conditions upstream of the shock has to be supersonic, that is Mach number should be greater than 1. Now this is a one dimensional flow, and there is no heat transfer or work done, so it is an adiabatic flow. Please make note, it is an adiabatic flow. As we do the equations, we will find out that shocks generate entropy. So it is not an isentropic flow, or it is not an isentropic process. So the basic equations that you have to apply here are the one dimensional conservation equations. This we have already discussed, and here one dimensional conservation equation is mass conservation, rho 1 u1 equal to rho 2 u2 is given over here. Then momentum conservation in one dimension, p plus rho u square is constant. So p1 rho 1 u1 square is equal to p2 rho 2 u2 square. Then energy conservation, h1 u1 square by 2 equal to h2 plus u2 square by 2. So these are the three equations along with an equation of state, and equations relating thermodynamic relations relating enthalpy as a function of pressure and temperature. This is the most general form, and an equation of state. So if you have these equations, you can solve for the these three equations. Now if you can see how many generally the upstream conditions are known. So pressure, density, temperature and velocity are known. So we solve for pressure, density, temperature and velocity. There are four unknowns here. There are three conservation equations, and enthalpy is related to pressure and temperature in a general form by some form like this, and there is a fourth equation of state. So we have a consistent set of equations. So this can be solved. This is the most general form. Here no assumptions are used, and it can be applied to any gas dynamic flow. So including if there are changes in the Cp and it is not a calorically perfect gas, you can apply these equations in that case also, but then you may not get closed form solutions in that case. So for this class we will seek closed form solutions, so we can understand something about the nature of these normal shocks, how they behave with changes in Mach number and so on. So we will take the assumption of a perfect gas and calorically perfect gas in particular, and let us go through the different steps to help us relate the various quantities. First thing that we would try to relate is the Mach number which is downstream of the shock to the upstream Mach number, and the relation is for a normal shock. A normal shock is normal to the direction of the flow, and for that it is always that the downstream Mach number is subsonic and upstream Mach number is supersonic. So how do we go about this process? So first we consider that the continuity equation rho 1 u1 is equal to rho 2 u2, okay, and the direct relation that comes about from here is rho 2 by rho 1 is u1 by u2. Now we can keep this, bear this in mind. Now second equation, so if you look at the methodology that is followed over here, you see that this process is completely simultaneous, or you have to solve them together. You cannot solve them separately. You still do not know any variables as of now, but we can through algebraic manipulations of these equations we can get to some relations which will help us to get to the final normal shock relations. So if you consider the momentum equation P1 rho 1 u1 square equal to P2 plus rho 2 u2 square, and divide this by the corresponding mass conservation equation. So I divide everything by the mass, but mass flow is constant. So I can divide this because rho 1 u1 is equal to rho 2 u2. I can do this, and on both sides of the equation. So I get these terms P1 by rho 1 u1. So this comes out as P1 rho 1 u1 plus u1 equal to P2 by rho 2 u2 plus u2. Now if you look at this and you identify the equations, here there is a combination P by rho, here there is a combination P2 by rho 2, and we know that for a perfect gas A square is gamma P by rho. So we will try to see how we can bring this information into this equation, and you can do that by multiplying and dividing by a gamma, and gamma P by rho is a factor here, this is one factor here, a group, and so you can write this as A1 square by gamma U1 plus U1 equal to A2 square by gamma U2 plus U2. Now at this you can even do a sort of change of, you can write this only in terms of U1 minus U2 is A1 square by gamma U2 minus A2 square by gamma U2 minus A1 square by gamma U1. Now here we can introduce using the alternate form of the energy equation, which is A square by gamma minus 1 plus U square by 2 is equal to A star square gamma plus 1 by 2 gamma minus 1. This is the alternate form of the energy equation that we had discussed in terms of the sonic quantities. So from here you can write A square is nothing but A star square multiplied by gamma plus 1 by 2 minus U square by 2. Okay, so now the process is just to use this in this particular equation, import it here, so you can get U1 minus U2 is star square. So here it is 1 by gamma U2 A star square gamma plus 1 by 2 minus U2 square by 2 minus A star square 1 by gamma U1 A star square gamma plus 1 by 2 minus U1 square by 2. So you get this equation over here. Now we will just consider just the right hand side for simplification and try to simplify that part. So let us look at this. So we will write it here. 1 by gamma U1 A star square minus U1 square by 2 minus 1 by gamma U2. It's the other way around. So let me just erase this. So 1 by gamma U2 gamma plus 1 by 2 minus U2 square by 2 and subtracted by 1 by gamma U1 A star square gamma plus 1 by 2 minus U1 square by 2. Now the principle being used here is this is an adiabatic flow. For an adiabatic flow the sonic state remains the same. So A star remains the same for both upstream and downstream flows. So this A star, this is constant across the shock. So we have now written it in terms of A star, and we can get quantities here, common, taking these common terms, gamma plus 1 by 2 gamma, we can get this 1 by u2 minus 1 by u1 plus 1 by 2 gamma and terms relating to u2 u1 minus u2. So if you look at the terms, you will get this term here, and on the right hand side you already had u1 minus u2, which was there over here. So this is equal to u1 minus u2. So now take this term over there. Okay, so A star square gamma plus 1 by 2 gamma u1 minus u2 by u1 u2 is equal to, so you have this term over here, and here you get the equation. Okay, so I have missed a part, which is, yes, at this point it is gamma minus 1 by 2 u square, so that term has to be included everywhere. So this is gamma minus 1 by 2 gamma, and so you get this term 1 minus gamma minus 1 by 2 gamma u1 minus u2. So this term turns out to be gamma plus 1 by 2 gamma. So you find the common terms are gamma plus 1 by 2 gamma u1 minus u2, and that sort of cancels out. You get a square by u1 u2 is equal to 1, or the other one is u1 u2 is equal to a star square. So if you divide this by a star square, you will get u1 by a star u2 by a star equal to 1. With this u1 by a star is something that we already know from our previous discussions. It is the star Mach number. So this gives rise to the relation m1 star multiplied by m2 star is equal to 1. So this relation is known as Prandtl's relation for the normal shock, and it gives us, so you can observe these manipulations, algebraic manipulations, where all the equations were used simultaneously to arrive at this conditions. And so just to go over these, so what we did was that we used the momentum equation and divided it by the mass equation, as you have done over here, and then written that equation in terms of the speed of sound over here, and then use the energy equation, the modified form of the energy equation, in terms of the star speed of sound and a star, and the idea is that a star remains constant in an normal shock, across a normal shock. So we use that information and import that into the equation here, and then do the simplification using some algebraic manipulations, and finally arrive at the condition that m1 star multiplied by m2 star across the shock equal to 1. So now we know the upstream Mach number, so this gives us a relation to find go ahead and find the downstream Mach number. Now this is in terms of star quantities, so we can convert this into the Mach number directly into Mach number, and that is possible. So this is all the steps are detailed in the slides which just now we have discussed. So this is what we finally arrive at, m1 star multiplied by m2 star equal to 1. So now let us look at how to get a single relation between this downstream Mach number to upstream Mach number. We use the definition of so m2 star is equal to 1 by m1 star, and so we can directly use the relation for m2 star, that is gamma plus 1 multiplied by m2 square and divided by 2 plus gamma minus 1 m2 square is equal to, so it is the inverse, so square is inverse of this, so you get the inverse, so you can put it here, 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. So now we solve this problem by solving it for m2 square. So you get gamma plus 1 m2 square is equal to 2 multiplied by 2 plus gamma minus 1 m1 square gamma plus 1 m1 square, and plus gamma minus 1 m2 square multiplied by 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. This term can be taken over to the left hand side, and then you can take the common term out, which is m2 square, and you have gamma plus 1 gamma minus 1 2 plus gamma minus 1 m1 square divided by gamma plus 1 m1 square. So if you solve this, this turns out to be gamma plus 1 whole square minus gamma minus 1 whole square m1 square minus gamma minus 1 2 divided by gamma plus 1 m1 square, and this value is 4 gamma, so that comes into picture here, 4 gamma m1 square, and you have gamma minus 1 remaining over here, and gamma plus 1 on the right hand side you have 2 plus gamma minus 1 m1 square by gamma plus 1 m1 square. So you have these terms are common, they will get cancelled. So finally the equation is just 1 plus gamma minus 1 by 2 m1 square by gamma m1 square minus gamma minus 1 by 2. So you find that m2 can be completely represented only in terms of gamma and Mach number before the shock. So now when we look at all other relations, shock relations, what we will observe is that all the properties across the shock can be written only in terms of the upstream Mach number and gamma. For the conditions that we are taking, which is calorically perfect gas, gamma is a constant. If you know the gas, then gamma is known. So then the downstream conditions of the shock become only the functions of upstream Mach number. So now we can relate. So now, since we know the relation between downstream Mach number and upstream Mach number, we can use this to relate all other flow variables. So let us look at first we look at the density ratio. So just to go over what we had just done, we have expressed the Mach number, that is Mach number downstream of the shock M2 in terms of only Mach number upstream of the shock and gamma. So we saw how to go about doing this using the Prandtl's relation. Now we will see how we can use the continuity equation to relate the density ratios across the shock. What we need is rho 2 by rho 1, and rho 2 by rho 1, that is density increases across the shock, and from mass conservation equation rho 1 u1 is equal to rho 2 u2, you directly get that u1 this rho 2 by rho 1 is u1 by u2. Okay. So now if you look and multiply and divide by u1, then you get this as u1 square by u1 u2. Now u1 u2 from our just recently discussed equations, u1 u2 is a star square. So this is u1 square by a star square. Now that is what is written over here, and u1 by u1 square by a star square is nothing but the star Mach number m1 square for the upstream flow, and star Mach number is written in terms of Mach number itself, gamma plus 1 m1 square by 2 plus gamma minus 1 m1 square. So now we see that the density ratio is also rho 2 by rho 1 is also only function of gamma and upstream Mach number. M2 is function of gamma and upstream Mach number. So just to distinguish, I can put this as F1 and F2. So we will now go ahead and do it for all other variables. So we have pressure ratio, we have temperature ratio, we have to look at what happens to stagnation temperature, pressure, entropy generation across the shock. So each of them we will go through in detail, and that we will do in the next class and see how these variables vary across the shock wave.